Hello, Nap. I couldn't hear you, so I will quickly reconnect. Okay. Hello.
Hello.
If you listen to me, I recommend that you mute me on Twitch and just listen from Discord. Okay.
Okay.
And interrupt me as soon as you have questions. I will try to double check if you understood everything. All right, let's start. Present. Okay. So the purpose of this lesson is to basically summarize the clean code lesson so far. Basically, essentially, all the lessons summarized into this one. I will try to re-explain what is solid, what is KISS, what is Yagne, what is drive principle, reintroduce again onion architecture, talk about boundaries, talk about configurability and design patterns, common design patterns, what's in common between all of them. So let's get right to it. Boundaries. So Nab, do you know what are boundaries in programming, in object-oriented programming?
No, I haven't heard it before.
So boundaries are essentially interfaces. They're abstractions, essentially. Highest level abstractions are interfaces, so you don't communicate with a specific, instead you communicate with a boundary, with an interface. You build a wall which separates implementation and the contract which you need to call. So that's a boundary. It's a gate between classes and layers. So usually boundaries are put between anything that has a behavior and between, and for filtering, let's say, functionality which is offered completely from the functionality that you need, that only you need, like use cases. Interface can implement use cases, and those use cases will filter out the functionality that you actually need. So why do we need them? It's probably self-explanatory and obvious, because we don't want to know details of what we need to call. We simply want to know what we need to do without knowing how. And that's the essential part of boundaries, essential role. When we know too much, and by too much I mean implementation details, we are sometimes maybe deceived, maybe spend too much time analyzing how it's implemented. We often don't need to know how. We need to trust something that we use and use it. And that's all. So the problem with code which always has a specific as a dependency is that it can fail. And if it fails, we might start having trust issues with code. Boundaries, the thing about boundaries is that they don't lie. I mean, it's a contract and it's simply a definition. You know what you need to pass and you know what you need to get or do. So that cannot lie. It's just a contract. The implementation can lie, but the contract will not. Thus, boundaries are a great thing for setting up trust for your code and being able to work around it if it doesn't work the way you want. So what do you think can be done when you need to basically work with code base which doesn't yet exist. I mean, what do you think should be done when you need to, let's say, call file upload implementation when it doesn't even exist? Basically, you want file upload service, but you don't have file upload service. You need to make an API which calls it, but you yet don't have the implementation for it. What would you do?
You're asking me?
Yep.
Sorry, can you repeat that?
So imagine that you need to call some code base, something which you should implement, but it doesn't exist yet.
Uh-huh.
So how do you work around this issue? Working with code which does not yet exist.
Well, I would call the non-existing code base as I would expect that it would work once I implement it.
And the keyword here is once you implement it. So basically you're referring to an interface, right?
Yeah.
Yes, so you would define an interface which does what you want it to. And this essentially is how test-driven development is based on. Basically, you have you write a test for code which does not yet exist. A test first approach. So boundaries interfaces define what we need to do. So we know what we want, but we just not yet know how we want it to be done, and that's fine. We call interfaces. So everything that has behavior should be put under an interface. The only thing in object-oriented solid-based program that shouldn't have an interface is a model, a DTO, or something like that. It shouldn't be interfaced because property implies on data, and it doesn't make much sense to have an interface for data. Another thing, another thing about interfaces is that we sometimes have predefined interfaces for third-party APIs. And such interfaces are good, they're usable, everything is fine with them, but sometimes we want, let's say, only some of it to be exposed, to be used. So we might need to be forced to implement the whole interface, but in our own application, we might want to use only a single method. So we could have our own interfaces as interceptors for third-party API and filter that out, the functionality with our own interfaces. Because we know what we need the best, not some third party, but we. So having our own interface and then adapting it is something to consider in some cases. And when we design our code, when we design how our code should be exposed, we should consider those things, how to provide interfaces without enforcing to implement something that isn't needed, to implement more than is needed. And I'm referring to interface segregation principle, the eye of solid. So yes, it's something to consider. Do you know onion, Nab?
No.
No. Okay, so do you see a picture?
I do, yeah.
Okay, so onion is an architecture which is a layered architecture. Basically, all modern architectures is based on some sort of n-tier. N-tier meaning that you have a separation for data access layer, for your domain layer, business logic, and for your view, your presentation layer. So for Onion, the beauty of Onion is that you have outer layer where you register all of the dependencies. You register all of the dependencies in infrastructure layer. In outer layer, you have basically stuff which has only calls to your implementation and registers your implementation, but it itself does not implement anything. It just consumes it. And the beauty of Onion is of two things. Thing number one is that Onion has no dependencies. It depends on abstractions and not on details, and that's the beauty of Onion. And another beauty of Onion is that it has a direction, a single direction, which points from outer layer to innermost layer. So infrastructure uses your application services, tests uses your application services, user interfaces uses your application services, your application services uses domain services, it might also use domain models, and domain services uses domain models. One thing to note here is that domain model contains objects, interfaces, contracts. It's a holder of abstractions which are needed throughout your application lifetime. That's the place where you want to put your interfaces and your models inside the application core, the domain model. That's where you hold your stuff, not where you use it. Like, you don't want to put domain services. I mean, you don't want to put an interface for domain services in domain services project. You want to put it in domain model because that's where your core, your definition of what your application can do resides, in the core, in domain model. So yes, and between each layer, like domain services call models, that's fine, but application services consume domain services through an interface, and infrastructure tests user interface consumes application services through an interface as well. So every layer is separated by a boundary, by an interface. And infrastructure is basically a dependency injection inversion of control container, like Unity, like AutoFac, like in Ninject. And this is how it looks like. Basically, you have a data service layer, which defines that you can get some generic entity with a defined interface, and a controller, a API layer, which consumes data service layer. Basically, API being your use cases implemented in a controller. For example, in general, my application can create, update, delete, and get entities, some generic entities. But for accounts controller, I can only create, delete, and get the accounts. I cut some cases down. I cut some cases off. Also, an API layer here, I put routing. How am I going to call my functionality? I don't just tell it to do it like this, but I also tell how to call it, how to reach it. That's what it also defines. How to access my functionality and how to filter it. More like how it's filtered. And other boundaries like third-party APIs, infrastructure, presentation layers, calls the API. What do you think about saying that we should limit freedom in our applications? What do you think it could refer to?
Preventing anarchy or something like that.
What do you mean by anarchy?
I think you refer to, encapsulating as much code as possible, and
Yes.
and preventing calls from being made across boundaries, essentially.
Yes, that too. But what do you think about code which is like super configurable? Like you can basically change every part of it, even though you don't have to, and you will rarely have to. What do you think about code like that? Through configurations and settings.
I'm not sure, actually.
So let's try to figure it out. There is a rule in clean code saying that configuration should be open in highest levels. For example, web config, app config is what highest level is. I mean, you don't even need to go to code in order to change some functionality. But when you think about it, if you put everything in such high level place, will it make maintainability easier? Will someone be able to maintain it anyhow easier?
Yeah, I can see that.
Yeah, and the answer is, like, if you really don't have to, you should either provide, if you seek for great configurability, you should either provide a default configuration so that someone doesn't mess it up, that someone can just provide no configuration and it will simply work. And if they want to override it, they can if they want to. But having too many options means that we have so many places that we can fail, that we can make a mistake. So we should consider that. For example, this is not really a configuration, but a class example how we give too many options for someone to fail. Like we have a filter and we have operation with some value, some filter. So what's the problem here? What do you think?
Yeah, essentially, as you said, we have too many options for the consumer to.
Yeah, and how would you fix this?
By separating the amount of the choices you can make.
More like limiting, I think, is the word you're looking for. Limiting choices, right?
Yeah, right, and separating them because
Okay.
there are several.
True. So how would you separate and limit the choices?
I would probably make separate classes for each of them.
I think that's an overkill for each operation. Imagine if this is, let's say, SQL filter. So you want the operation to be translated to SQL comparison operand, like equal, less, more, less equal, less, more equals, and so on. So class for each operation would be an overkill in this case. So there's a better way. And that better way is having an enum of operations. And basically, when you want to consume this, you could have a dictionary for which operation, which enum operation translates to which string literal. So that's how you would bind the operation name to its translation value. And like you said, it's separated and it's limited to a selective few options.
Yeah, I see. Yeah, obviously.
Yep. So with too much configuration, we have many problems where it can go wrong. The biggest problem is over-engineering when it comes to too much configuration. Sometimes it's simply not needed. So we should seek to keep it simple and stupid. Or small. That's how it's called as well. And a good example of how also we can limit configuration is having a subclass which holds a configuration of a parent class. So let's say we have the following case. We have a shape parent class which holds edges. Like a shape is defined by a collection of edges. And we build a shape by passing those edges. Square is also such shape. Maybe it has some more things. Maybe we also define how we calculate area of a shape of a square. Maybe we just define how we render it. But that's not the point. The point is that it's also a shape, and all we want is to set edges somehow. And same for rectangle. But those two cases for square and rectangle construction are bad. They are bad. Why? Why are they bad?
You tell me.
They're bad because square is how many edges? 4. Square has 4 even sides and 4 edges. The problem with this constructor is that we can pass more than 4 or less than 4 edges. So it doesn't make sense to have such freedom for a square. It should be limited. For rectangle, we are passing 4, but we don't really need to pass 4. We need to pass basically bottom left and top right, not the other two, because it is that's how a rectangle works. And for square, all we need to pass is a pivot point, like bottom left, and length of a side. And then we can determine the places of other edges. So we need to consider how it works, how the shape behaves. In other words, we need to have prior domain knowledge in order to understand how we can limit the freedom that we gave to the user. So the refactored version would look like this, where you limit the options to just 2 for rectangle and to just 2 for a square. For rectangle, you have 2 vectors for 2 points defining the edges, and based on those edges you can get other edges. And for square, in the same analogy, except that instead of 2 points you have 1 and length of a side, so that you can determine where the other edges are. So only by having a good understanding of our domain knowledge we can have such limitations. We can restrict freedom in a user-friendly, understandable way.
Mm-hmm. Makes sense.
Yeah. And one Johan from our Discord said, well, he quoted Rightfold is a member of another C# Discord. He quoted that person, and I love the quote. And it goes like this. He said that if we seek for flexibility, we achieve complexity. And if we seek for simplicity, we get free flexibility. So by seeking for flexibility, like lots of configuration, like it works in many cases, you have little code and it does magic, it just works, we create complexity. Like this, we create complexity. And we shouldn't design systems which are super flexible. We shouldn't have a mindset that they're flexible to use. We should have a mindset that they're simple to use. Because simple means extensible. Simple means they are easy to use or easy to reuse, easy to understand, easy to change. Ease of use is what we should aim for when designing systems, not flexibility. Now let's move on to another topic, and this topic is about testability, but I would like to look at it from a different point of view. Unit tests in general, not only tell if our program works. That's what they are for initially, but another thing about unit testing is that it allows us to give, like, if we have everything under testing in our program, in our application, that means that the code quality is good. So in order for code to be testable, it needs to be modular, doing one thing. And that is only achievable when code quality is quite good. So testability is a measure for good code. So we should not only think that test is great for checking if our code works, but we should also think that it's helpful because it enforces those best practices for our code to be robust, decoupled, modular, and small. That's why writing a test is another benefit, other than just checking if our code works. What do you think should be under testing? What should we test? Also, hello to whoever joined.
I think we should test behavior.
Behavior. Okay, that's true. So let's say you have a behavior under test. Let's say you have file import under test, and your file import has, let's say, a method called import, and it takes a file as an input, but you refactored that method, and you have many more classes. Would you test those classes too after the refactoring?
So do I test all the classes that's involved, or?
Yeah. Or that's a byproduct of what after your refactoring, like you tested behavior and then you thought that you can make code cleaner by splitting it into smaller pieces, and
Oh yeah, I see.
So would you test it?
Yeah, I don't think I would test every method unless I deem it necessary.
Yes. So what should be tested is not functions nor classes. It should be features of our program.
Mm-hmm.
So something that happens post refactor, it should stay there, not under test, unless it is big enough to be considered a behavior of its own. So what if you can't test? What do you do if you cannot write a test for your function or your behavior?
Well, you should try to think of a way you can make it work with a test.
Yeah, so you refactor it, you split it, because that's an indication that something is wrong with your code. If you cannot write a test for it, it's probably having some smell in it. Something is wrong.
Yeah.
And the paradox about refactoring and writing tests is that basically the picture sums it up. If you have a legacy system which has no tests, and then you suddenly want to write tests, you suddenly read about it, you started to like it, it's a paradox because you cannot really start testing it. It costs quite a lot of time it takes a lot of effort to test something that wasn't tested initially. So with because when you refactor something, so maybe some legacy system is dirty, but it doesn't have tests, and you want to refactor it, but you cannot refactor it because it doesn't have tests. Because if you refactor it, you might break it. So you need to have a way to test if it still works after your changes. But you cannot because you didn't write tests. And that's why not having tests is such a bad thing, because you're starting being afraid of a change or refactoring, and you're being left with worse and worse and worse code later down the line. So that's the illustration just sums my point up completely. Tests serves one more purpose, and you can write tests for learning. Let's say you work with something that you don't know, like a third-party library that you never used, and it doesn't really have great documentation. So through experience, you understand how it can be used. A rule of thumb is that we should not test third-party code, third-party API. We should presume that it's already tested. We should have that trust. But if it's not clear how it works, if we don't understand how it works, we can and should play with it. We should experiment with it. We should write tests for it, because like that we can have results for learning which are in some material form, which are well defined, clear in tests. So for some really like shady, not clear, or unspecific third-party APIs or your colleague codes, if you have no other way of learning them other than reading documentation or asking about it, you should write tests for it. Don't be afraid to test not your own code if it helps. Testing it, learning it through unit tests is a good way. And almost last topic today is design patterns. And I would say traditionally composition means that you basically can compose of similar type, basically have a relation of parent and leaf. Like basically parent is being composed of its own parts. But what I mean by composition, and what I think everyone means when they talk about composition in general, is that it's basically having many small modular pieces of code, like classes, where you have a module, and by module I mean a class, so many small modules in some container class, and that container class exposes those private modules through public methods. That's what I call composition. And why is the king of patterns? Because the king of object-oriented programming is inheritance, polymorphism in general. And inheritance is a dependency, and we don't want dependencies in our code. We want to limit them. And that's why when it's convenient, when there is no loss, when there is little benefit of inheritance, we should prefer composition. We should prefer composition over inheritance, because with composition, we can have interfaces as dependencies and not concrete parent classes. Another nice design pattern is a factory. It's for creating something similar. Like here you can see chess pieces are being created in Piece Factory. So we can either have some property which defines what piece we want to do, or we use a type, generic factory, for saying that we want a knight or a pawn. So we can either provide an enum or a generic for creating something from a factory. It's done two ways. Singleton is the third pattern that I would like to cover. So, Nab, do you know what singleton is?
Yes.
Do you use it?
I have in some cases, but mostly I try to avoid it.
Okay, so why do you avoid singleton? In one word, could you sum it?
Is it what do you call it? I can't find the word.
Well, basically, nobody likes global state, and singleton is global state, just like static. So singleton is global state, and that's why it should be avoided. But there are cases when it's useful, and when it's useful, I mean, in cases where in cases when we are forced to use static, we should use singleton instead. I mean, cases when there is a state involved, not just some helper method, but a state involved, then we should use a singleton. It helps. For example, if you want to have a transition of a soundtrack between scenes in Unity or some game, singleton helps. If you want session, for example, you have I think session is also kind of a singleton, because you have HTTP context, and then you have current, and current is like an instance. Like there's only one current session, so there's like a singleton of HTTP context, and then you can have a HTTP context current session to get a session of a current user. So singleton. So singleton is nothing more like static, which with a global state, except that singleton is extensible, and singleton is a dependency that we can control. We can have an interface for a singleton, but we cannot have an interface for a static class, because we need an instance for something to be interfaced, and static has no such thing. And another benefit is that with singleton we have only one static instance of a member, one static member, and with static class we have all static members. So it's nicer to have a limitation to a single static thing. And again, should be avoided, but if needed, it's not a bad choice. So strategy is another pattern which helps to avoid if statements. When we have countless cases where there is something which influences our control flow based on a property or something else, we can prefer polymorphism over if statements. And basically what we can do is extract those lumps of code in if cases and put them in another class. And we can have a factory which basically handles how those classes, objects responsible for behavior is being created. The good thing about this is that we can have polymorphism. I mean, we have polymorphism in if statements. I mean, instead of if statements in some behavior, but you might think that our factory is just a bunch of if statements, but that's not really true, because all our factory does, it picks behavior based on those if statements. I mean, it just picks a behavior, but behavior itself is extensible as it is contained in an object which is unrelated to other if statements. So we have a separation for each behavior which is called in an if statement. So let's say if you have a VAT calculation based on a country, you could have a factory which builds VAT calculation formula based on a country input. And then you just build an object which is basically a formula. And then you just execute the formula with an input and you get a VAT instead of having a bunch of switch or if-else statements. Lastly, another great interface design pattern is an adapter. And this coming back to a point where I said that you can have your perfect interfaces, adapter helps. Basically, what adapter is that you have an input and an output. And basically you have 2 points, something that you submit and something that you accept, receive. And submitting output and receiving input should be the same, but there are cases when it's not that. This is extremely useful. So in those cases, we use adapter, some proxy, which simply converts input into the type of output that we need. So that input is the same type that we want to receive. That's an adapter. And the great thing about adapter is that we can implement our own functionality and then simply have an adapter which adapts that functionality to some legacy system. So we can have modern solution for old problems using old systems, but using it would simply come into a form of an adapter. We wouldn't do anything except mapping basically our processed models into legacy models. I had to do this at work when I wanted to basically refactor legacy system, make it with interfaces, make it fluent, make it easy to understand and use, and I used adapter. I implemented my stuff in my way, in how I think is clean and good, and then I used adapter to adapt my model to model of a legacy system, and call it from legacy system, map it to legacy system. So adapter helps a lot, especially in old legacy systems. And what unites all design patterns is abstraction, encapsulation, polymorphism, and those three are essentially pillars of object-oriented programming. So other than that, it's best practices, design rules, and now let's talk about design rules. Clear intent is what design patterns define. Clear intent is when reading code is telling what it does. You don't need to look into implementation details to understand what it does. It even should tell how it does it. Well, not quite, but it should imply in some way at least. So clear intent means being loud at what you want to do, but being silent about how you do it. Those are the two things that clear intent tells us to do. And naming things right is the most important part of clear intent. For example, you have words which are synonyms for creating an object. You can create an object, you can build an object, you can save an object, you can make an object, but basically each of those words have their own intention. If I create an object, I expect the method to return void. if I save an object, I expect it to handle a case for checking if it exists, and if it exists, it gets updated, and if it doesn't exist, it gets created. If I have a method called build, I accept an object to be returned. So there are many words which you can pick for having the same meaning but a more clear intent. And inheritance as a design choice is something that you should rather not do if you can, and you should prefer composition over inheritance. It's a design rule that you should follow, because like that you will avoid dependencies that you don't really need, and you will avoid cases, you will limit the cases where you need to where you might have a chain of inheritance. You don't want a chain of inheritance. You want to limit to one or at most two parts of a chain, but not more than that, because it's dirty and hard to maintain. And another rule of inheritance is that if we see code that is similar and that does the same thing, and if we think that we might change it via a parent class, like reuse code via parent class, we should think twice, because we shouldn't reuse our code semantics. That's not what inheritance is for. Inheritance is an is-a relation. It's not uses a relation. So inheritance should be used to inherit logical relations, to have logical relations, to have relations which don't really change. Like you have a human female and a human male, and they're both humans. So you can use inheritance in those cases. But let's say if you have a design where a robot female and a male female comes in, then you cannot really inherit from a human, because you need for robot to do the same, and you cannot really, because robot is not human. So inherit logic but not code semantics, logical relations. Dry principle, illustration says it all. Dry principle is basically saying not to repeat yourself and keep a single place for a single change. Like if you want to change something, you should know exactly where to look for it, and it shouldn't be split into two places. If you want to change a single thing, you should look into a single place. And if you look at multiple places, that's a code smell. Specifically, it's called shotgun surgery, where you have a split modules which contain basically the same functionality except split between multiple classes. And when you need to change one, you change all of them. And medicine for it is simply combining those modules into one single class, merging them basically, like a composition of them. So writing everything twice, in other words, wet is annoying. And there is a rule, lazy rule of 3. Even if you use a code block, let's say you call something which has 30 symbols in a line, but basically you repeat the same 30 symbols 3 times. So if you repeat them 3 times or more, you should refactor those 20 plus symbols into a function that you can reuse 3 times instead of calling the same long line 3 times. It's a lazy rule of 3 because as soon as any code duplication happens, like once, if you repeat the same thing twice, then you should consider refactoring. But if you repeat it 3 times, it should be as a rule. It should kick in as a lazy rule of 3, and you should tell yourself to, hey, it's repeating too much. And if I will need to change, I'll need to change 3 places, but I'm lazy and I want to change 1 place only. So refactor until a change happens in a single place. Lastly, I think maybe one more slide is about solid, and just quickly repeating. Solid is single responsibility. So Nap, do you know solid principles?
Yeah, somewhat.
Okay, so can you tell me letter S, single responsibility? What does that mean?
That a class should only have one reason to change.
Okay, great. But it also works for a function. For a function, what does it mean?
A module or a unit should only have one responsibility in the program. It shouldn't try to handle several things.
Yes. So what is doing one thing in a scope of a function?
What doing one thing means?
Yes, for function.
It means it should do exactly what it's supposed to do and nothing else.
Okay, so is it doing one thing if I have a function called check error and log if it fails? More like check error and log it. That function. Check error and log it.
No, that would be a violation. I would.
So every time when you need to check for error and log it, you would call it two functions basically every time instead, right? Okay, so it's not really what doing one thing means. Highest level functions like this basically means for a function to do one thing, it means that you don't mix levels of abstraction. So different levels of abstraction means that you don't, let's say, do a for each loop with processing and then call a high level function after it. You don't mix those two. You should split the for each loop into a function and call that another function afterwards. And in the case that I said, where you check for error and log it, is a fine case. I mean, you don't want to repeat yourself. You want to keep your code dry. You don't want to repeat yourself. So it's fine to have functions which do more than one action, but it still does only one thing if you don't mix levels of abstraction. And another indication of how you can say if it's a level of abstraction or not, if you split function many times until there's nothing more to split, and in that case, if I want to log and if I want to check an error and log it, and if that calls two functions, that's not a bad thing, because if I want to do those two things in one call, I cannot split it even more to refactor it. So that's what doing one thing for a function means, is having as high possible level of abstraction in that function in order for it to work. That's doing one thing for a function. What is OpenClosed Principle? How can you explain?
I can only repeat the textbook definition of it, basically.
Okay, so go ahead.
It means that a class should be open to extension but closed to modification.
Yes. So this rule and the whole solid basically means that you want to limit the amount of changes that need to happen to things which already work. If you design If you design something which already works, you don't want to touch it. You don't want to change it if you don't have to.
Yeah.
So how do we do it? How can we achieve? How can we implement extensibility?
Well, the main thing I can think of is inheritance.
Yes, and that's the classical approach to the problem. And it was like in the 90s. In the 90s, they would use inheritance to extend already working functionality. But the problem with inheritance is that it like I said, causes the stacking dependencies, and it is a way, but there is a better way. And what is a better way than inheritance?
I can't think of any right now.
So if we have a concrete implementation and then it breaks, or if we want to swap it with another one, what do we do?
If we want to swap the implementation,
Yeah.
We define an interface for it.
Yes, so having external changes for already working classes is done either through inheritance or dependency injection. There are two ways. So like that, we define behavior outside of something that consumes it. So we limit the changes like that.
Right, yeah.
And the third one, Liskov Substitution, what does that mean?
It means that I forgot the word, but derived classes should be substitutable with their parent classes without the code breaking.
Yeah, and in simple man's words, it basically says that you shouldn't fake child classes that inherit parent. So it's quite simple, because it becomes dirty too soon, too fast, and you should consider it if inheritance is the way, and that's why composition is a preference. So how do you refactor something that breaks the principle?
I would need to look at the context first.
Well, if you have a rule, prefer composition over inheritance, so how do you refactor?
Sorry, I wouldn't know.
So by splitting. In general, refactoring is usually splitting something. So by splitting and composing the parts into another entity, container composition is how you can refactor it, so that you use only a part that you need instead of a whole package. Interface segregation, what does that mean?
It basically means separation of concerns, but for interfaces. Like it's better to make more interfaces that and inherit from more of the interfaces, so you can build on more behavior, instead of having just one big interface that encapsulates everything you need.
It's partially true. So there are 2 points to this one. It basically means OpenClosed Principle except for interfaces. And what it means is that you shouldn't touch working interfaces, published interfaces, because other people use them and they already have implemented contracts which you defined at some at some point. So you don't want to redefine working contracts because it breaks other people's implementation. So how you avoid this is by extending interfaces that are already working and adding behavior there, or designing interfaces to be atomic, meaning that they do a single operation per interface. So by default, you don't force anyone to use a big interface, but just a small part of it. So 2 ways how you can achieve it. Dependency injection, inversion. What can you tell me about it?
I think I'm using your words now, but basically that lower level implementations shouldn't depend on higher level implementations.
Yes, and
like that.
Yeah, and this is not my words. These are words, I think, of Uncle Bob, Robert C. Martin. So basically, the problem with having a chain of dependencies is that if any part in a chain fails, the whole chain fails, and you don't want that. And another thing is that if you want to have a quick fix or change the whole thing, or a part of it, it will be hard because you have a dependency chain. But if you have an interface, you can now have a one-on-one dependency where a class depends on an interface. So every class depends on an interface and nothing more. And by default, such dependencies and a one-to-one dependency and something that is easily changeable, swappable, fixable, understandable. And that's what inversion of control is all about. And because instead of stacking dependencies from highest level module, which we depend on, to the lower level modules, which the highest level module depends on, instead we have a dependency to an interface. And if you know UML, interface relation, if you use an interface, it's a use relation. But if you implement an interface, it's an implements relation. And then when you put an interface in between a specific concrete implementation and a class which uses that implementation, so now it uses an interface, you invert the direction of flow of dependencies, all dependencies pointing to an interface. So like this, you no longer have a chain, rather a one-to-one relation. And it's great for that reason. It's great because it eases testability, and that's actually where its practical use comes to. Because when we need to test something, we no longer need to implement all the chain of dependencies. We can simply mock it at ease. So that's inversion of control. Dependency injection is basically registering a concrete implementation in our inversion of control model. Like when a class depends on an interface, we can register through a constructor or a method or a setter that which implementation, which concrete implementation we want to use. And that's called dependency injection. Keep it simple, stupid principle is basically a mindset that we should think about another person. That when we code, we shouldn't think that it works and it's good enough. We should be empathetic towards someone else. We should think about the other person. So we should think how to make code to be easy to use for another. And if there are cases where you write your own code and you don't understand it yourself, you should stop and refactor it. Because simple leads to flexible. Simple not only for you, but for everyone. And that leads to flexibility. Lastly, Yagni. We basically don't want to use things that we don't need to. And if you cannot remove those things that you don't need to, at least hide them or split them. And I would like to emphasize a point here about internal access modifier. For example, if you have a bunch of classes which are related, but only make sense to be related in your project, but outside the exposed relation, the exposed properties wouldn't make sense, then you should split them, then you should hide them. So a good way of hiding it would be writing internal. So if you write internal, it means that you hide it from public use. I mean, outside the project, it will be invisible. Inside the project, you need relations. You can use it because it's internal. Internal to the project, those properties and classes are public. Outside, they're private. That's why it's useful. So too many choices, too many things that are exposed lead to too many mistakes. And there is a nice saying which sounds like that we should maximize the time, the work which is not done. So we should think what we need and do only that, because otherwise we're wasting our time on things that we don't need. So to sum everything up, I would like to put all those principles into solid, dry, not wet, Yagni, KISS. So I wish you all to have such KISS and apply all those design rules. Because when you apply those design rules, design patterns simply become obsolete. I mean, maybe ambiguous. I think the best word, they're becoming deprecated. I mean, all of it should come naturally. When you apply those rules, you will see that eventually, hey, I use this design pattern. I didn't even know that such pattern exists, or that it has such name that I use. But hey, I just applied the rules and it came naturally. That's what will happen if you apply the rules. So do a solid, dry, not wet Yagni KISS, and your code will look sexy. So write sexy code. And that's it for today. Do you have any questions?
No, not really.
All right.
Thanks, though. It was, I think it was an awesome lesson.